Hello, welcome back. So today we're going to continue on and talk more about functions. So I'm going to very quickly begin by reintroducing or redefining a function and then talking about one-to-one and on-to functions, and then we'll move on with some applications. So let's start with functions. We said from the very beginning that the definition of a function is that every input has one and only one output, and we call the input set A, we call the output set B. So every A has one and only one output. And the way that we can define that is we can say every A, every input has at least one output and it has at most one output. So we've defined those individually, number one and number two, and for it to qualify as a function, both of these statements must be true. So in effect, we have an and statement that links these two things, or an and operation that links these two things. So that is called a function. On the other hand, we have what's called a one-to-one function as well. So this is defined after it is defined as a function. So you have to first identify this as a function, and then you can figure out whether or not this function is one-to-one. And the definition of one-to-one is that every output, every B, has at most one A, has at most one input. And our definition here is as such, and you notice that this is actually very similar to the second part of the function definition, with the exception that the A's and B's are switched. So one-to-one means that every output is used at most once, so it cannot be used twice. So a counter example for one-to-one would be if we see an instance where we have two inputs go to the same output, that's not one-to-one. We also have an onto function, which is every output has at least one input. Every B has at least one A. So a situation here or a counter example here would be that if I find a B1 that doesn't have an input going to it, or another way to say that is if we find something in the codomain that is never used, that is not in the range, then this is not onto. So again, our onto definition looks a lot like number one, part one in our function definition, with the exception that A's and B's are switched. So we then said that there are some rules governing one-to-one and onto functions. It could be that a function is both one-to-one and onto, but for that to happen, the size of the sets must be equal. So that we called a bijective, one that is onto and one-to-one, a function that is onto and one-to-one. And we said the sizes have to be equal. Now, furthermore, we also made a statement that if the size of A is bigger than the size of B, then there cannot be any one-to-one functions. Just because if the size of A was bigger than the size of B, there's a guarantee that there's an object in B, there's an object in the output that has to be used at least twice, right? And similarly, if the size of A, so we were talking about that one. So similarly, if the size of A is less than the size of B, then there cannot be any onto functions because there will have to be one item in set B that is never used. Now you see in this example, it was the object A, so object A was never used, but in general, there's a guarantee that there's at least one object that's never used in such a case because you're only going to see three arrows. So what that means is when in the next slide, when we talk about one-to-one and onto functions, we have to be careful to identify that uh, that this equation or this scenario that we're working in only applies when the size of A and the size of B are in terms of their relativity. So for example, for me to have a one-to-one function, it must be that the size of A is less than or equal to the size of B. And for me to have an onto function, it must be that the size of A is greater than or this greater than or equal to the size of B. So let's do a few examples on counting. Now, again, you might find these a little bit helpful, but in general, we have the techniques already to count the functions that we can see. So for example, I have a couple questions here. How many different functions are there from set A to set B? So let's just do this. Now, when I mean different functions, what I mean by this is let's say I have one, two, three, and then I have A, B, C. Okay. So by different function, I mean that the mapping is different. So for example, I have a function that can go like this. Okay. So one goes to A, two goes to B, three goes to B. That's a function. A different function would be something like this. If I instead made two go to A instead, so that would be a different function. So another different function would be if I made 3 go to C. That would be another different function. So how many different functions are there from set A to set B? Now let's set up some variables. Generally, I'm going to call the size of A is equal to M and the size of B is equal to N. So you can imagine a situation where we have a bunch of inputs, right? So A1, A2, A3, for example, and we might have B1, B2, B3, and B4. Okay, so here our M would be 3 and our N would be 4. Okay, now we want to define the number of functions that's in this case. So let's imagine that we have a function and we're defining a mapping that goes from A1 to somewhere, from A2 to somewhere, from A3 to somewhere, all the way up to AM goes somewhere. So when I say go somewhere, it means one of the B's, one of the outputs. Okay, so for example, if I look at A1, in this example, how many choices do I have to draw this arrow from A1? And the answer here is 4, right? In fact, it's equal to n. So there are n ways to fill this box. Okay, so here notice that all we're asking is how many different functions are there from A to B. There's actually no constraints. We don't care what type of function it is, as long as the arrow goes somewhere, that's the only definition of a function. So there, the first box, we can fill it with n different choices. The second box, we can also fill with n different choices. So after we pick one of the outputs for A1, for A2, we again have n choices because any of these choices can be reused over again, right? So in fact, I can have a function in which all of the A's point to B1 or all of the A's point to B2. I can have a function like that. So for example, I can have something like this, right? That is an example of one of the functions. Okay, so there is repetition that is being used here. And I use this term, and I hope you can think back to our counting section and kind of remember what type of algorithm or what type of formula this is. So again, N3 is n choices, all the way up to M is n choices. So in fact, we have n times n times n, m times. The answer here is m to the power of m, which I'm just going to say is the power of, size of b to the power of the size of a. Now try to remember this. Size of b to the size of a is measuring how many functions I have given the size of the sets. Okay, so given the size of the sets, how many different functions can I create? Keep this in mind because we're going to actually use this equation a little bit later on. All right, so that's how many functions. Well, what about the second part of this? And I'm going to use a different color here. The second part of this asks how many one-to-one functions are there? Oh, by the way, before we move on to the second question, let's identify what type of question this is. This is the same equation as our permutation with repetition, right? And it makes sense because we are placing the B's into the boxes that represent A's, right? So it's just like we have M boxes and all those M boxes can be filled with any of the N B objects, right? So this is a permutation with repetition. Well, what about the second question? The second question is how many one-to-one functions are there? Well, I think I can use the same setup, right? We can still have a function where we have A1 goes somewhere, A2 goes somewhere, A3 goes somewhere, and so on, all the way up to AM goes somewhere. And this time, the only difference is that if this is a one-to-one function, if I use one of the outputs, I cannot use it again. Remember, the definition of one-to-one means every output can be used at most once, right? At most one. So that means I cannot use it again once I've used that output. So if we ask the question, how many different ways are there to fill that box if we kind of delete all of this, right? So let's say A1 goes to B2. Okay, now that means B2 can no longer be used. So there's n ways to fill the first box, but the second box, there's only n minus 1 ways, and then n minus 2 ways. And then all the way up to we have n minus essentially m minus 1 ways, right? So if you imagine the relationship here is n minus 0, n minus 1, n minus 2, and then here we have n minus and then m minus 1. Okay, so I hope you can see kind of the relation here, but this actually works out to be n minus m plus 1. Okay, so I'm going to leave the equation like that. So so if you take this equation and you keep multiplying it, you will get actually n factorial divided by n minus m factorial. Okay, so imagine that I take this multiplication. So I'm going to multiply n by n minus 1 by n minus 2 all the way up to n minus m plus 1. If I take this multiplication, let me just write it like this, and I keep going. So multiply by n minus m, multiply, 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 all the way down to 1, and I divide by the same thing. This essentially is going to get me the same answer. So that's why we get this as an answer, n factorial over n minus m factorial. Now, again, if this formula looks familiar, it's because this formula is a permutation without repetition, right? Where we had n total objects, and this time our group size is m. Okay, so let's get one quick question out of the way, which is, when I multiply this all the way down, is it possible? So I stop at n minus m plus 1. So is it possible that where I stop is a negative number? Okay, so you have n minus 1, n minus 2. I stop at n minus m plus 1. So is it possible that n minus m plus 1 is actually a negative number? Because if that's the case, then our equation doesn't really make too much sense, right? And I'm here to say that it's not possible for this to be a negative number. So in fact, it's not possible for m to be bigger than n. Okay, so for this number right here to be a negative number, it would have to be that m is bigger than n, which is not possible. Now, if you think about why that is, it's because here we're dealing with one-to-one functions, right? So we're dealing with one-to-one functions. The preface of this, if we go back a couple slides, is that size of A has to be less than or equal to the size of B. So we have to say that the size of A is less than or equal to the size of B. That's the assumption that we make before we can calculate the number of one-to-one functions. So that means that the m has to be less than or equal to the n. Now you might say, well, what if you give me a situation where the size of A is bigger than the size of B? Well, then according to this, we have no one-to-one functions, right? So if I give you a situation where the size of A is bigger than the size of B, then right away the number of one-to-one functions is 0. Okay, so let's be clear. Size of A is bigger than the size of B, the number of one-to-one functions is 0. If the size of A is less than or equal to the size of B, then the number of one-to-one functions is given by this formula, which is nothing more than a permutation with repetition. Okay, so those first two questions actually are pretty straightforward, right? So I think we can all see from our discussion on counting before how this equation comes about. Something that we haven't really talked about, at least in too much detail, is the number of onto functions. Okay, so it turns out that there's a class of counting problems that we didn't really talk about yet, which is the application of onto functions. Now let's review. What is an onto function? So let's go to the next slide here. So what is an onto function? And let me do this in blue color. So let's say I have A, B, C, and D as input, and I have 1, 2, 3 as an output. In fact, let's start a little smaller. Let's go A, B, C, and then 1, 2. Now, uh, in this scenario, an onto function means that every output is used at least once, right? So one example of an onto function would be this one. Okay, that would be one example of an onto function. Another example of an onto function would be if I put b over to here. So that would be two onto functions. And what we want to do is find a way, a formula in order to calculate the total number of onto functions given the size of A and the size of B. Now, let's get this out of the way right away. So what is the assumption that is made about size A and size of B when there's an onto function? So let's go back here. For an onto function, the size of A has to be bigger than or equal to the size of B. So the size of A has to be bigger than or equal to the size of B, which according to what we were talking about before is the, oops, is that the M is bigger than or equal to n. So we had our size of A is equal to m and our size of B is equal to n. Okay, so this is the assumption this time, just as we go through this formula. All right, so let's go with this definition. So let's say we have a set A and we have a set B. Okay, so now I want to answer the question, how many onto functions are there in this case? So probably the best way to count the number of onto functions is take a look at any cases that are not onto. Okay, so are there any cases that I can think of in this set A and set B which are not onto functions? Well, I can actually think of two. So you see if you can think of those two. It turns out that this, if all of the inputs go to just the item 2, that's not onto. Okay. And another one would be if all the inputs go to only the output 1, that is not onto. And those are the only two cases that are not onto. So what I'm going to do here is I'm going to identify all the functions. Okay, so what are all the functions that are in here? Well, as we saw before in the previous slide, all the functions is size of B to the power of size of A. So size of B to the size of A. Okay, and I'm going to subtract those ones that are not onto. Now, in this case, there are just two of them. So there's the one where A goes to only 1, and there's A goes to only 2. Okay, where all the arrows go to 1 or all the arrows go to 2, those are not onto. So there's only two of them in this case. Okay, so I'm just going to take the size of A, the size of B to the power of size of A, so 2 to the 3 minus 2, which is going to give me 6. So the answer here is 6. We have 6 onto functions going from 3 items to 2 items. Okay, now you might be saying, well, that's quite simple. Why did you say that we haven't done this type of counting before? Well, it turns out that if you increase the size of the output, this problem becomes significantly harder. So let's do another example here. And I'm going to now give an example of A, B, C, and D, so 4 items. And then the output is going to be 3 items. So we have set A and set B. And this time, we want to figure out how many onto functions are going from set A with 4 items to set B with 3 items. Okay, let's use the same strategy that we used in the previous example. So I'm going to take all the functions. Okay, that one's easy enough. I'm going to subtract off those that are not onto. Okay, so now it becomes a little bit harder because in the previous question, all we did was we covered up one of the objects, right? So first I said, okay, let's pretend one isn't there, right? All of the items go to two. And then I covered up the number two and I said all of the items go to the number one. And and those functions are not onto. So here, can we do the same thing? So let's pretend that one is not there. Okay, so let's pretend this object is not there. I want to find out how many functions go from the set A, so this is our set A, to only the set 2, 3. Okay, so I hope you can agree that if I take all of the items in set A and I map them to only the set 2, 3, that all of those functions are not onto in our scenario. Okay, so just take a second just to convince yourself that if I take the input A and then I map them only to the objects 2 and 3 without the 1, any of those functions are not going to be onto. Okay, now how many functions are there of that type? We'll talk about that in 1 second. But that's not all, because even though I just covered up the 1, right, there is another scenario, which is what if I just cover up the 2? What if I don't use the 2? That means if A goes to only the set 1, 3, once again, none of those functions are onto. Okay, there's another scenario where I cover up only the 3, right? And I consider A goes to only the set 1, 2. None of those functions are onto as well. Okay, so we have to identify all of those. Okay, now let's just start counting. So what about all functions? How many all functions are there? Well, size of B to the size of A. So here we have 3 to the power of 4. And now I'm going to subtract. Now notice that we have 3 cases. Okay, so our 3 cases is that we have this one, and this one. So we have 3 times, and each one of these cases has size of B to the size of A different functions, right? Size of B to the size of A different functions. So here we have size of B is 2, and the size of A is 4, right? So notice that we're mapping the set A to only the set 2, 3. And then we're mapping the set A only to the set 1, 3. And then we're mapping the set A only to the set 1, 2. And each of those outputs only have 2 items in the output. So that's why this is 2 to the 4. And there's 3 of them. Okay, so we have 3 times 2 to the 4. So are we done? Well, the answer is no, we're not. Why? Well, because let's say you consider all the mappings from set A to 2, 3. Okay, so I'm mapping only from A to 2, 3. Would you agree that one of those functions is this one right here, where I map every item to 3? Okay, that's one of the functions that I have right here. Now, do you also agree that when I do the same thing here, that this is also one of the functions? So in fact, I've subtracted this function too much. I've subtracted it 2 times, right? So you see, this function that I'm looking at here was subtracted in this case. It was also subtracted in this case. So I've subtracted too much. What about the one that maps A to only the output 2? Well, that one I've also subtracted too much. I've subtracted it once here, and I've also subtracted it once here, right? So you see, I have an overcount of the subtraction. And in fact, there are 3 overcounts of the functions. The one where A goes to 1, the one where A goes to 2, and where A goes to 3. Those were all subtracted too much. So what do? I add it back. Remember inclusion, exclusion? So I have 3 of these types and 1 to the power of 4. So remember, size of B to the size of A. So how many of these are there? There's size of B to the power of the size of A. And now I hope you can start to see a pattern developing. So we have 3 to the 4, and then 2 to the 4, and then 1 to the 4. And all along, we're doing subtract, plus, and so on. Okay, so can we derive an even bigger pattern out of this? Well, I think we can, because if you think about where this 3 comes from, okay, the 3 comes from the fact that we have 3 cases where the A goes to a subset of size 2. right? The A goes to a subset of size 2. And why is this a 3? Well, it turns out that this 3 is nothing more than 3 choose 2, right? So from the 3, so from the set B with 3 items, I choose 2 of them. Why is it choose? Because it's a set, right? It's a set, it has no order. So from the 3 items, one, two, three, I choose 2 of them. And there are 3 ways to do that. Okay, what about this 3? Where did this 3 come from? Well, it's from the fact that we have 3, choose 1, right? So 3 choose 1. From those 3 items, I choose 1 item. Now, if you can see the pattern here, you can imagine that there's actually a 1 in front here. So this is actually a 3 choose 3. Right? If you really think about it, all the functions just means that I'm not taking any subset of the outputs. I'm using everything in the output. So it's really a 3 choose 3. So now I hope you can start to see a pattern developing for our number of onto functions. All right, I'm going to go to the next slide, and I'm going to show you a general equation for the number of onto functions. Now, as I write this out, don't get too don't get too scared because this function is quite long. But you'll have this during an exam or anything like that. But furthermore than that, I will talk later on in this lecture about a really fast way in order to calculate this. Okay, so even though I'm writing out a really long equation right now, know that there's a fast way to calculate this really long equation. Okay, so here it is. Given that we have the size of A is equal to M and the size of B is equal to N, our assumption here is that M is bigger than or equal to N. Okay, so our size of A is bigger than, or sorry, let's go back here. Our size of A is bigger than or equal to the size of B. Okay, so let's take the first part, which is I'm going to take all the functions. Okay, so all the functions is n to the power of m, size of b to the size of a. I'm going to put an n choose 0 at the front. Okay, so n choose 0. Actually, not n choose 0, n choose n. Let's do that. Okay, and then I subtract n choose n minus 1 and then n minus 1 to the m. Now, if you take a look back at our previous example, this is analogous to 3, choose 2. So take one item away from the number of outputs we have, right? So cover up one of the items. So that's what we have here. And the number of functions that we have associated would be n minus 1 to the power of m. And then we add, take away 2 items. So n choose n minus 2, and then n minus 2 to the power of m. That's how many functions there are of that type, right? So I cover up 2 items. And then I subtract by covering up 3 items and 4 items and so on. So this is going to alternate plus, minus, plus, minus, plus, and then all the way down to eventually we're going to get -1 to the power of n minus 2, n choose 2, 2 to the m plus -1 n minus 1, and then n choose 1, 1 to the m. So this is our full equation. So just verify that this is what we get. Now this -1 to the power of something is to guarantee that we have a minus plus thing going on here. But if we kind of shorten the summation here, we're going to get the summation as equivalent to the sum from k equals 0 all the way up to n of -1 to the k, n choose n minus k, and then n minus k to the m. Now, just verify very quickly that, in fact, this summation works out to this equation. So I just want you to verify that. Now, it turns out that this equation is the number of onto functions. So this is the number of onto functions from A to B, given that the size of A is equal to M and the size of B is equal to N. So take note of this. This is something that you probably should know, uh, at least in this section. All right. So what is a nice application of this? Because in the previous couple of applications, in the number of functions as well as the number of one-to-one functions, we're probably able to figure out a question of that type because we have the permutation with and without repetition. But what is a question of this type, the number of onto functions? So there is an application here. In fact, I'm going to show you two applications very quickly that are quite related to each other. One is distributing m distinct objects. Now, the word distinct means different. Okay, so I want to distribute m different objects into n different containers such that each container has at least one object. Now, just take a second very quickly that such a question is referring to an onto function. So let's go back here. Okay, so I want to fill uh, 4 items. I want to put 4 items into 3 boxes. So 4 items into 3 boxes so that each box has at least one item in it. Okay, so that type of question is typically referring to an onto question. Okay, so if you take a look to the left here, we have a question. How many ways are there to give 6 different sandwiches to 3 kids so that each kid gets at least one sandwich? All right. So let's pretend that we have two sets. Okay. We have the set A, which are the sandwiches. We have 6 different sandwiches. Okay. So S1, S2, all the way up to S6. So what that means is if you get the first sandwich, that's different than getting the second sandwich and the third sandwich and so on. All right. So maybe the first one is a ham sandwich, second one is a cheese sandwich. You get the idea. Right. And then we also have these 3 kids. So we were distributing to kid number one, B1, B2, and B3. Okay, we'll call them, these are my kids. These are my 3 kids, B1, B2, and B3. I think that's probably the name that I'm going to give my kids if I had 3 kids. So, uh, so I'm going to distribute these 6 sandwiches to the 3 kids. And the extra constraint here is obviously I don't want any of my kids to be hungry. So every kid has to have at least one sandwich, right? So right there, we have an onto application. We're distributing inputs into outputs, right? So our outputs being the kids, inputs being the sandwiches. So, well, we have the equation here. We have the size of A is equal to 6 and the size of B is equal to 3. And so according to the equation that we just put in the previous slide, the solution here is k equals 0 up to 3, so up to n. Sorry, this is m and this is n. Okay, so the k from 0 up to 3, -1 to the power of k, and then we have n, choose n minus m, or minus k, and then n minus k to the power of m. Now, of course, this is going to be a pretty long summation, especially if the size of your sets gets larger and larger, right? So notice that the number of terms in this summation does depend on the number of objects in B, right? So the bigger the set B, the more summation that you have to do. Now, if you work out the summation, it turns out that the answer here is 540. Now, how was I able to figure that out? Well, it turns out that there's a very nice equation to go with that. I'm going to talk about that a little bit later. Uh, not right now, but a little bit later. But right now, I want to give a kind of another look at an onto application. So take a look at this question that we just did. We have 6 different sandwiches given to 3 different kids so that each container has at least one object that's in there, right? But let's change this question a little bit. How many ways are there to put 6 different sandwiches into 3 identical bags so that no bag is empty? Okay, so now we just changed the output a little bit. So they're no longer kids, right? So remember we had 540 as an answer here, right? So they're no longer different kids, they're actually identical bags. So let's take one scenario. One scenario is that we have B1 with sandwich 1 and sandwich 2, and then we have sandwich 3 and sandwich 4 given to B2, and then we had sandwich 5 and sandwich 6 given to B3. So let's say this is one of the scenarios. So there's actually along the lines of these distributions, there's uh, there's actually six ways that we can rearrange this. Now, what I mean by this is that I could just as easily have given S3 and S4 to B1, and then S1 and S2 to B2, and then S, uh, S5 and S6 to B3. Okay. Now notice that when I said the answer was 540, I've indicated that these two are different. These two are different answers, right? But in my new problem, notice that these two distributions are exactly the same because the bags are identical. So the only thing that matters is what goes in the bag, right? So which sandwiches go in the bag? That's the only thing that matters. So distinguishing from B1, B2, and B3 is not necessary. And in fact, you might agree with me that I can draw up 3 factorial identical distributions in this case. Okay, so just please make sure that you understand what I said there. I can keep doing this. I can keep listing all of these distributions that are the same. I can list out 3 factorial of them. Why? Because there's 3 factorial ways to rearrange B1, B2, and B3. So essentially, in the problem on the right-hand side, we are getting rid of this order. There's too much order here. We're getting rid of that order. So the answer here, the question on the right-hand side is going to be 540, but I'm going to divide it off by 3 factorial. Now notice 3 in this case is the size of the output. Okay, the size of the output. So, so there's 2 questions that I want you to be wary of here. Distributing different objects into different containers so that no container is empty, distributing different objects into identical containers so that no container is empty. So there's two different questions that I'm asking you here. Okay, so this one was the one in the previous side. Like this one was the left hand side. This one was the right hand side. Okay, and they have different solutions. However, those solutions are related to each other in the divided by n factorial. Okay, so notice here that I have the equation for the number of onto functions. If I use that equation and I divide it by n factorial, I will get the problem on the bottom. Okay, now it turns out that this equation is a very special number. It's a number called a Stirling number of the second kind. And the Stirling number of the second kind, we typically label it as SMN. Okay, the Stirling number. Now, why is it that we discuss the second type of question? Because you might imagine that the second type of question is quite rare. That type of counting problem on the right-hand side, that's very rare that we need to calculate that. But it turns out that Stirling numbers are special because they have a very nice equation associated with them. So if you take a look at this right here, we have, whoops, sorry, the next slide. So we have a relationship. S of m plus 1n is equal to S of m n minus 1 plus n times S of mn. Now, again, the Stirling number S of mn is measuring the number of ways to distribute m different objects into n identical, so same containers, such that none is empty. So each container has to have at least one object inside. All right, so I'm just going to take a look at this thing right now, and when we come back from our next video, I'm going to show you exactly how this equation works. Okay, so once again, this chart is telling you that if I have let's say 5 objects, and I have 3 containers to put them in. Okay, so how many ways can I put 5 different objects into 3 identical-looking containers so that no container is empty? The answer: 25. Okay, I can read it right off this chart. Okay, so the good thing about this is that now if I want to know the number of onto functions from 5 to 3, the answer is just n factorial is just 3 factorial times s of 5, 3. So the number of onto functions from 5 to 3. Okay, so from inputs, 5 inputs to 3 inputs is 3 factorial times s of 5, 3. Now you might be wondering, how did I get 3 factorial there? Let's take a look at the equation one more time. So, so you see the difference between the Stirling number and the onto function. So this is the onto functions, right? This is the Stirling number. The difference between the two is this thing right here, right? So if I already know the Stirling number, how do I get back to the onto functions? I need to get rid of this part, which essentially means I need to multiply n factorial with it. Okay, so I need to multiply n factorial, those things will cancel out, and the only thing I'm left with is the equation for the number of onto functions. So let's see if we can formalize this. The number of onto functions from set A, from A, with the size of A is equal to m, to B, where the size of B is equal to n, is n factorial s of mn. So remember this equation. Okay, so if I know the Stirling number already, I can easily find the number of onto functions, and I never have to expand that summation, right? So, well, that all comes down to the fact that how do we use this, or how do we find this this table of S of mn? If you take a look at it closely, it does look a lot like Pascal's triangle, doesn't it? Okay, in fact, it works exactly the same way as Pascal's triangle, except with a different equation. Okay, so when we come back, when we go into the next video, I'll show you how this equation works and how we can find this triangle based on the S of mn. Okay, so I'll see you in the next video.